we have these three types of energies. We have PEG, PEE, KE. Now they stand for potential energy, gravitational, potential energy, elastic, or kinetic energy. Those are the formulas, and by asking these questions for each energy helps us identify whether that energy is present or not present. So they're meant to be yes/no questions, and if the answer is yes, then we have that form of energy. If the answer is no, then that value is 0, and we can cancel that type of energy out. So for PEG, or gravitational potential energy, the question we ask ourselves, is there a height? Does that object have a height? If h is equal to 0, then there's no height, there's no gravitational potential energy. If there is some height, then there is some value for PEG, and we'd have to calculate what that is. For PEE, potential elastic, we're talking about springs, bungee cords, rubber bands, racquetball poppers that we're going to make. And then we have compressed. Is there a compressed or stretched spring? Now, it doesn't have to be a spring, but it's stretchy, springy stuff. We're going to skip those for a little bit. We'll come back to those. And then, is the object moving for kinetic energy? Does the velocity equal 0? If the answer is yes, if there is, the velocity is 0, then there's no kinetic energy. If the velocity is something, then it has some kinetic energy. Now, when we talk about velocities, remember velocities have directions, and sometimes we use positive and negatives to define a direction. And if we have a velocity that is -2, and we put it in our KE equation, it'd be 1/2 mv2 squared. I'm sorry, v squared. So it'd be -2 squared. I know you guys know what -2 squared is, and your calculator will tell you what -2 squared is, but those numbers could be potentially different. So be mindful of that if you plug in a negative number and you square it. Because what is -2 squared? It's 4. It's positive 4. But I'm guessing that if you on your calculator go -2 squared, it's going to tell you that it's -4. And I'm not exactly sure why it's taking the opposite of 2 squared. Maybe because it's not in, I mean, you can, if you put in parentheses, then it's good. So just be mindful of that as we move along. So by answering those questions helps us identify whether those forces exist or whether they don't exist. We're going to get into two basic types of problems here. We're going to have one location problems and we're going to have two location problems. And when we have a one location problem, the question generally being asked is how much energy does an object have at a location? At a location. Okay? I thought I fixed them, apparently I didn't. On the worksheet you picked up, it says how much energy. I thought I switched them to how much mechanical energy. I thought I changed those, apparently I missed a couple. So if it's a one location problem, I'm asking the question, how much mechanical energy does an object have at a location? And mechanical energy is the sum of all your potential and kinetic energies, and our formula is listed like this. Now my formula that I wrote on the board is slightly different than the order that I wrote it on your formula sheet. But they're additions, so I'll try to be consistent, but I might mix up the orders. And as long as you are okay with it, I'm okay with it. Well, I shouldn't say that I'm okay with it. Hopefully you are okay with it. But it's the addition of three things, so if I go 1 plus 2 plus 3, it's the same as if I go 3 plus 2 plus 1. Right, so the order in which I add three numbers doesn't matter. So sometimes I switch those KE, PEG, PEEs around, but I try to be consistent. So if we're simply going through and saying how much mechanical energy does an object have at a location, I'm asking how much kinetic and potential gravitational and potential elastic, and add those three numbers together to solve for ME. Tomorrow we'll start looking at two location problems. And a two location problem is where we compare how much mechanical energy we have at one location to a second location, or even a third location, or a fourth location. But we only ever compare two locations at a time. So when we start looking at two location problems, then we start using that equation on our formula sheet that says work in plus work done by friction is equal to our change in mechanical energy. Now on your formula sheet, I tried to show it to you. When we talk about delta, right, that's the Greek symbol delta, it means change. And when we talk about a change in something, it's always the final minus the initial. So if I said, when I left school today, it was 5 degrees, and now it's 15 degrees, what was the change in temperature between when I left and now? Well, you take your final minus what you started with, and that'll give you your final, your change in temperature. I don't remember what I said. Did I say 15 and 5? So our change would be 10, okay? But now if I'm going to say, well, right now it's 10 degrees, and at 10 o'clock tonight, it drops back down to 5, and at 10 o'clock tonight, I say, well, what was the change in temperature since 2 o'clock? Then you take your final temperature, 5, minus your initial, you get a negative 5. And that's significant, that negative versus positive tells you whether gained or lost something. So on your formula sheet, to the right of forces, I put a delta equals final minus initial. That's a very general statement, but it's when we talk about change in something, it's your final something minus your initial something. So if we talk about change in temperature, it's your final temperature minus your initial temperature. If we talk about change in mechanical energy, I talk about my final mechanical energy minus my initial mechanical energy. So in 1D and 2D motion, we talked about initial velocities and final velocities, and I used VIs and VFs. Instead of using VIs and VFs, what I start doing is I start using V1s and V2s. It's just another way to note that. But the nice thing is, if I talk about location 1 and location 2, VI and V2, and then all of a sudden I change it to, I'm going to compare V2 to location 2 to location 3, I can still keep V2, and I can just add a V3. I don't have to say, well, what was VF is now really the VI. I don't have to kind of do that semantics of what's the I and what's the F. So I start using 1s and 2s instead of that. And we'll start talking more about that tomorrow. But this is the equation that we use when we start getting into 2 location problems. And then with those 2 location problems, we start talking about like what is the final velocity after this, or what height will it get to. So we're going to start by practicing some 1 location problems. And our 1 location problems that we're going to go through are found on the in-class energy worksheet that you picked up on the way in. So on in-class energy, question number 1, quick pictures are helpful, I think. And when we draw pictures, we're really looking for types of energy. So we're looking for PEG stuff, PEE stuff, and KE stuff. And when we talk about PEG stuff, masses are good, heights are good. When we talk about PEE, we're talking about spring stuff. Spring constants, how far that spring is stretched or compressed. And when we start talking about KE, we need mass. We already had mass. And then velocities. So things that are good to put on your pictures are mass, velocities, heights, and spring stuff. We're not going to talk about springs yet. We're just going to say, is there a spring, yes or no, and then we'll move on from there. So if we read question number 1 found on in-class energy, it says, how much energy does a 15 kilogram block have that is traveling at 15 meters per second? So how much mechanical energy, I thought I fixed it, it should read how much mechanical energy. How much mechanical energy does this block have? The first question, is this a 1 location or 2 location problem? Am I comparing how much energy it had at 1 location versus the other? Or am I only looking at 1? It's a 1 location, so it's at ME equals question mark is how I kind of note this. So I'm trying to solve for ME. So the equation we use to solve for ME is ME is equal to KE plus PEG plus PEE. So that's the equation we're going to be solving for. And we're going to solve for this. So we go through our 3 types of energies. We ask ourselves the questions that go along with it, and they're intended to be yes/no questions. If the answer is yes, we keep it. If the answer is no, we cross it off because the value of that is 0. So for KE, the question that is asked, is this object moving? And is this 15 kilogram object moving? And we know it's moving because it has a velocity of 15 meters per second. So is this object moving? The answer to that question is yes. So this one is going to get kept. We're going to keep that one. We're going to have to solve for that. For PEG, the question for PEG, is there a height? No, it doesn't mention anything about a height. So because there's no mention of height, we can assume that it's not changing. We're really looking for changes in height once we get to two locations, but no heights listed, so we can say, well, then there must not be any PEG. And then for PEE, is there a compressed or stretched spring? No, it doesn't even mention the spring, right? And just for the record, we won't have a spring for a couple days. But that's where we're starting. So I do this a little bit different than I think we did like our forces. When I did forces, we drew free body diagrams. I put a bunch of numbers directly on the free body diagrams, and then in Newton's second law, I put the numbers right into Newton's second law. This one I tend to like start with this, and I do some substitutions. Officially, it's a substitution. But instead of saying ME is equal to KE, I write the formula for KE. So KE is equal to 1/2 mv squared, right? Because KE is equal to that. So instead of writing KE, I write 1/2 mv squared. And if I wanted to, I could say plus 0, but I think we're probably all at points where we can say, we don't really need those. And I'm solving for ME. Now, along the way, we will be able to do some simplification. We'll be able to cancel common variables. But we're not there yet. Just for the record, what does this M right here stand for? That's mass. What is this M representing?
Mechanical.
The M in the word mechanical energy, right? So is this M the same variable as this? No. Okay, just so we're clear on that, those are two different M's. So we're solving for ME. ME is equal to 1/2 the mass, which is 15, times our velocity, which also was 15. And we take that and we can square that value. So if we go 0.5 times 15 squared, we get an overall value or an answer of 1,687.5, and all of our energies in works are measured in joules. So 1,687.5 joules is how much mechanical energy this 15 kilogram object has that's moving 15 meters per second. Remember, there is a squared next to that velocity. Sometimes people forget that, but there is a velocity squared. Why don't you try number 2? How much mechanical energy does the object have? Is what the question is asking. Take a moment, you try number 2. So it's an ME equals question mark. Does this object, 2.5 kilogram object that's moving at 25 meters per second, does this object have kinetic energy? Is this object moving? Yes. Gotta keep it. Does this object have PEG? Does this object have a height? Nope. Value is 0. Does this object have PEE? Is there a compressed or a stretched spring? No, no spring even mentioned. So in this question, all of the mechanical energy this object has comes from the kinetic energy, and we calculate that by taking 1/2 times the mass of that object times the velocity of that object squared. ME is equal to 1/2 of 2.5 times 25 squared. Our value 781.25 joules. 781.25 joules. Good? Okay, let's try the next one. This one's a little bit different. Still, it's a one location problem. So if we take a look at question number 3, question 3 says, how much mechanical energy does a 5.6 kilogram ball have that's 3.5 meters above the ground? So I have a 5.6 kilogram ball that is 3.5 meters above the floor. So when I draw my pictures, I'm looking for masses, velocities, heights, spring stuff. And I try to label as many of those things as I can. So I have my mass, it's 3.5 meters off the floor, so that's a height. Looking for V's, looking for spring stuff as we go. So ME equals question mark, it's a one location problem. Mechanical energy we calculate by taking KE plus PEG plus PEE. And now we start asking ourselves the questions. For kinetic energy, the question is it moving? And the response to that answer, your question is no. So my kinetic energy is 0. PEG, our question is there a height? And is there a height? Yes. We got to keep it. I underline them, I don't know why, but I keep them. Okay, PEE, is there a compressed or a stretched spring? Nope, no spring mentioned, right? So ME, all of our mechanical energy comes from PEG, which is M times G times H. Our mechanical energy is 5.6 times 9.8 times 3.5. Our mechanical energy, the sum of all of our energies is, by definition, mechanical energy. 5.6 times 9.8 times 3.5 is 192.08 joules. Why don't you try number 4? Here's my picture, 2.4 kilograms, 4.2 meters tall. That's my height. It's a one location problem, ME equals question mark. How much kinetic plus gravitational plus potential elastic energy? We ask ourselves a question, KE, is the object moving? Which you would respond?
No.
So therefore, that's 0. PEG, the question is there a height, which you would respond?
Yes.
Yes. Keep it. PEE, the question is there a compressed spring, which you would say?
No.
So we cancel it out. So ME is equal to M times G times H. And hopefully you went through, and as you did 2.4 times 9.8, 8 times, you should have gotten a value of 98.784 joules. Why don't you try this next one, number 5. You try it, assuming it goes well, this will be our final one that we'll go through today. How much mechanical energy is the question? Picture, hopefully your picture looks similar to my picture. I'm looking for mass, heights, velocities, spring stuff. Those are things would be good to put on our picture. So I have a mass, I have a height, I have a velocity, don't have any spring stuff, because there's no mention of a spring. From there, by identifying these things, should help you identify these things. So I'll pause for a moment and let you try from there if you haven't. So, questions, KE, is the answer yes? Is it moving or not moving? Yes or no? I'm sorry, that was not a yes or no question. The question should be, is it moving? Yes. Okay, so we keep KE, there's a V, right? So we gotta keep it. For PEG, is there a height? The answer is? Yes. So we gotta keep it. Is there a compressed spring?
No.
No, so we can cross that off. So my KE is 1/2 mv squared. My PEG is m times g times h, and we have to add those two values together. Order of operations, do the multiplication before you do the additions, just to be clear. So ME is equal to 1/2 the mass of 2.5 times the velocity of 3 squared plus our mass of 2.5 times 9.8 times our h, which is also 2.5. Yep, okay. So our mechanical energy is the sum of those two numbers. The first number, the kinetic energy number, 1/2 times 2.5 times 3 squared is 11.25. Our potential gravitational energy, when we add those, or multiply 2.5 times 9.8 times 2.5, we get 61.25. And then when we combine those two together by doing the addition, we get a total mechanical energy of 72.5. So if it's a one location problem, we're just going through and determining how much ME is there. How much gravitational and kinetic and potential elastic does this number object have? We find their values, we sum them up. That's what mechanical energy is, the sum of our potential and kinetic energies. And then we can get our overall values. And what we're doing here, there are some problems that we'll do like this, but ultimately this is like the start of, this leads us into two location problems when we start talking about the changes in mechanical energy. But in order to determine the change in mechanical energy, we have to determine what is the mechanical energy at those two different locations. Okay, so this is a homework sheet, it's called Conservation 1. I have not introduced how to do all of these problems yet. But the first 5 problems, the first 5 are problems that you should be able to do at this point. And I've done enough talking at you over the last couple of days that I think you and I would prefer to not talk the entire class period again. So the first 5 problems on the worksheet called Conservation 1 is the start of a homework sheet. We'll end up doing all of this at some point. The problems that we were working on called in-class energy are exactly meant to be that in-class problems that we will work on together. So don't worry about those. But problems 1 through 5 are one location problems. So with our time remaining, we're at a good point where you should be able to probably finish these first 5 problems. Maybe you can start working on number 6, maybe not. I'd hold off on number 6. But then we'll be ready to kind of hopefully transition into 2 location problems starting tomorrow. So as you work through these, if you have questions, please talk to me or your friends and let us know what we can do to help.